Few announcements. The first is a reminder that you have a midterm a week from today. It's going to be in class, so it'll replace the lecture that would usually take place. It's going to be 5 questions, and each question is going to be like a short written exercise. Let's see what else I can tell you about it. I don't anticipate for it to take the full 80 minutes and for it to be like a, terribly difficult exam, but the TAs are taking it now to verify that. I'm going to release, as a practice midterm, I'm going to release the midterm from last year, and I'll put that up on Blackboard. I ask that you don't share that, just like the homework solutions. Please don't share that with anybody. That's why it's not on the course website. It's because I don't intend for that to be public. It's just for the purposes of this course. So I'll put up the practice, as a practice midterm, I'll put the midterm from last year's course as well as the solutions. So you guys can take that this week. You are allowed 1 sheet of notes, front and back, as small font as you want. I don't care. You guys can make it size 1 point or something. I guess that's it. Anything else I can tell you about the midterm? Besides the questions, of course. Yeah.
Maybe what's the balance between computational and theory?
Well, you're not going to do any programming in the midterm. It's all written. It'll be like the level of homework question in the sense that the theory will involve checking something that involves, a little bit of convex analysis or subgradients or something of that sort. And if there's anything that's algorithmic, it'll be asking you to describe an algorithm rather than implement it. So it might say, like, what are the steps of, write out the steps for Newton's method for this problem or something. So just checking that you actually could give us, concrete a description as possible of the algorithm, but no implementation, obviously. OK, so Thursday of this week, there's not a regular lecture. I decided to make it a review session, so it'll just be I have a table that it's actually already on the course website, a table that summarizes all the algorithms that we've learned so far. And then I don't have any planned lecture after that, so we'll just take questions. So if you have open questions about stuff we've learned so far, you can ask them on Thursday. OK. So this is our last lecture for the second order method unit. And we're going to talk about Proximal Newton method. It's kind of a nice thing to finish on because it ties together the proximal operator, something we learned when we talked about first order methods, but also with the power of Newton method. So just to remind you, last time we talked about the Primal-dual interior point method, I thought that was actually, it was a rather difficult algorithm to learn in the sense that it's fairly technical and I don't think it's very intuitive, but it's an extremely efficient algorithm. And in terms of interior point methods, it's pretty much the state of the art for interior point methods. Of course, there are like a bunch of variations on the Primal-dual interior point method that people think about. And I even said there were whole books about the Primal-dual interior point method you could read. But we at least saw kind of the framework for what a good implementation of a Primal-dual interior point method would look like. And the idea is to just take an arbitrary problem, convex problem, where the constraint functions and the criterion function are doubly smooth. And consider writing down the KKT conditions, but then perturbing complementary slackness so that instead of having ui times hi of x being equal to 0, as we usually would in complementary slackness, we change the right-hand side to -1/t. That was the jumping point for this Primal-dual interior point method. And we chose the sign of this right-hand side appropriately because ui is always going to be positive and hi is always going to be negative. That's primal and dual feasibility. So to say that this is close to 0 but not quite 0, we'd have to say that it's actually -1/t, something small and negative. So the Primal-dual interior point method, it basically takes these KKT conditions, which it tries to solve for a particular value of t. And to do so, it actually linearizes them. So it writes down the KKT conditions as a solution to this system. It's a nonlinear system in x, u, and v. Try to set this equal to 0 and solve it. That's just the KKT conditions without the inequalities. And it linearizes this. So it comes up with a linear approximation to this system, and it solves that linear approximation instead of the original system, and it repeats it over and over again. And each time it solves this, it actually updates t to be something a little larger, and then solves the linearized version of the KKT conditions again. Okay, so the updates are similar to those for the barrier method, but it's often faster. It's faster than the barrier method. And I didn't draw this picture last time. I feel like maybe I should have, so I'll draw it now. So remember, the barrier method, what it does is that it kind of smooths out the constraints. So we saw this picture of like a polyhedral constraint set. Suppose you're solving an LP. The contours of the barrier function maybe look something like this. So there's smooth versions of the polyhedron that that might be the constraint set for the LP. And then it starts at some point in the interior. That's why these are called interior point methods. It starts at some point in the interior of the constraint set, and it solves the smooth problem. And then it essentially relaxes the penalty that you have on the constraint so that they become less and less smooth as the algorithm carries on. So remember, we saw that it traced out a path that looks something like this. Maybe that was the solution to the LP. It traced out a path that looks something like this. That might be the solution. OK, so this actually can't quite be true because the path it takes, we saw, is always perpendicular to the contours of the barrier function. So I didn't draw that great, but I think you get the point. This might be the central path from the barrier method. And to get a point in the central path, we iterated Newton's method until convergence for that particular smooth problem. That's the barrier method. So how come the primal-dual interior point method is more efficient than the barrier method? How can it do that? Well, one way to think about it intuitively is that it stemmed from a realization wherein we didn't really care about getting very accurate solutions at intermediate points along the central path because we didn't iterate Newton's method until convergence. We just took one step of Newton's method, and then we updated t, and took one step of Newton's method and updated t, and so on. And so its path really looks something more like this. Okay, so it doesn't care about getting these intermediate solutions correct. It doesn't iterate Newton's method until convergence. It actually is off the central path for its entire course of the algorithm's life, its lifespan, but it cares about getting the eventual solution correctly to high accuracy, and that's what it does. So if you take a course which teaches interior point methods in more detail, they will make this concept more precise, and they will talk about neighborhoods of the central path. And actually, they will prove that the primal-dual interior point method remains in a certain neighborhood of the central path as the algorithm carries on. And different types of updates give different guarantees. So the one that I gave, the Newton's method update I gave, I believe it has a guarantee of some form. It's within an L2 neighborhood of the central path. But those are details we didn't cover. This intuition, though, about not iterating until convergence at intermediate points along the central path is maybe helpful for remembering why the primal-dual interior point method can be more efficient. Okay, because it doesn't actually stay on the central path. It jumps around in the neighborhood of the central path, but eventually it converges to high accuracy at the point we want it to, which is the solution. Okay, questions about that? So we're going to talk about proximal Newton today. We're going to recap proximal gradient descent, and then introduce proximal Newton, and then we'll talk about the usual things, backtracking, convergence analysis, and some notable examples. So just to remind you, hopefully you haven't forgotten, or if you have forgotten, then you'll relearn this for the midterm. Proximal gradient descent is an algorithm that applies to problems of this form. I want to minimize the sum of two functions, g of x plus h of x. So my criterion splits up into the sum of two functions. And g is convex and smooth, and h is convex but non-smooth, with the assumption that it's simple. And by simple, we mean that its proximal operator is explicitly calculable. That's what we mean by simple. So the proximal gradient descent updates for minimizing this criterion are to choose some initial point and to repeat these iterations. Xk is equal to the proximal operator. This is defined in terms of h, applied to the gradient update I would have made on g. So I'm at the point xk minus 1. I take a gradient descent update with respect to g alone, some step size, and then I apply the proximal operator of h, and that gives me the iterate xk. So how do we define the prox? The prox operator associated with some function h at the level t is given by the argmin over all z of 1 over 2t times the L2 norm squared of x minus z plus h of z. Okay, so it's trying to find a point that's both makes h small, but that's proximally close to x. That's why it's called the proximal operator. And this t, this constant t, or this parameter t of the proximal operator, it controls the strengths of those two terms. Okay, so we saw that this prox operator, it is explicitly characterizable for certain norms, for example, or other functions. Like, for example, for the L1 norm, we actually proved that the prox operator was just given by soft thresholding at the level t. So I go through every component, and I just either subtract t or add t if it's positive or negative. And if I'm ever going to be moving through 0, I set it equal to 0. That's soft thresholding. We proved that. If h is the L1 norm, that's soft thresholding. We also looked at the proximal operator for the nuclear norm, or the trace norm, rather. I think on the homework you did other examples as well. So you can calculate this for a lot of different functions h. And the beauty of proximal gradient is that the difficulty in these iterations now computationally, assuming you can compute the gradient, is only determined by h. So if for example, if you knew how to solve L1 penalized least squares with proximal gradient, then immediately you know how to solve L1 penalized logistic regression. And there's no difference in terms of the expense there per iteration, because each iteration is really determined by the proximal operator, and that doesn't depend on the smooth part g at all. It only depends on h. Okay? So the high-level recap is that it enjoys the same convergence rate as the fully smooth version. So gradient descent corresponds to the case when h is 0, and it's useful when the proximal operator is efficient. Okay, that was proximal gradient descent. So what was the motivation for proximal gradient descent? Now this becomes important, now that we've learned second-order methods. The motivation, remember, was that we thought about this as this proximal update. So this is literally the proximal gradient descent update. I take where I was, x. I take a gradient descent step in the direction of grad g, or negative grad g. That's this x minus t grad g of x. And then I evaluate the proximal operator at this point, which means that I find the z that minimizes this criterion. This is just evaluating the proximal operator at the point x minus t times grad g of x. That's my proximal gradient descent update x plus. So that's just writing out the update a little more explicitly. If we expand this, just expand this and throw away the terms that don't depend, say, on z, we get grad g transpose z minus x plus 1 over 2t times z minus x squared. That's what I get by grouping these two terms together and then expanding the square, and then just h of z. So what do I recognize this as? This is like a quadratic approximation to the function g, but where I've used the Hessian equal to 1 over t times the identity. Okay? I could also put in g of x here. I could put, it's the argument over all z of g of x plus grad g transpose z minus x plus 1 over 2t times z minus x squared. That g of x is not going to affect the argument, so it doesn't matter. And so what we recall is that the motivation for proximal gradient is that we take our smooth part g, we form a quadratic expansion of g, but in the Hessian, in place of the Hessian, we stick in 1 over t times the identity matrix, and then we minimize that plus h of z. Okay, that was the motivation for proximal gradient. Now let's recall what the fundamental difference between gradient descent and Newton's method was. Remember, there was a big difference between those two. They both are motivated in terms of quadratic approximations, but Newton's method actually used the appropriate local Hessian for that quadratic expansion. Right? So Newton's method actually, instead of using this expansion, so that was the gradient descent expansion. Newton's method kind of one-upped this in a sense and used a better quadratic expansion, a more accurate one, which was given by the actual Hessian matrix of G at the point x, this guy. So now the natural question to ask ourselves is, what happens if I do the same thing but within the proximal operator? What happens if, instead of just taking this very simple quadratic expansion where I use 1 over t times the identity for my quasi-Hessian, the thing that would usually go there, what happens if I actually use the full Hessian? So I replace this term, the quadratic term, with z minus x transpose Hessian of g z minus x. What would we get? And that's called Proximal Newton method. So that's the name we attribute to that, Proximal Newton. And it's really just exactly this, but replacing that quadratic term with a quadratic in the Hessian of g. That's all it is. And we could also write it more like proximal gradient by defining something called the scaled proximal mapping, or you might call it the H proximal mapping, just because we think about it now it has a matrix H as a parameter, not just a constant, but actually a full matrix H as its parameter. So if you give me a convex function H, I define its scaled proximal mapping to be the argument over all z of 1/2 x minus c squared in the H norm plus h of z. And this H norm is defined by, that's a typo, I don't know why I wrote x transpose z. The H norm is defined by just a quadratic form in H. It's exactly what you'd expect. Okay, so that's what we call the scaled proximal mapping. And if we take H to be 1 over t times the identity matrix, we get back the usual proximal operator, unscaled. So what's Proximal Newton method? It's exactly what we'd expect given our previous motivation. The slide is motivating it. We just initialize some points. We take y as the result of applying the scaled proximal operator to a gradient, actually to a Newton step, rather, with respect to the criterion G, where this hk minus 1 is just the Hessian of G evaluated at xk minus 1. So this is the result of applying our scaled proximal operator to a full Newton step on x, xk minus 1. And then this is a direction. We treat this as a direction to move in. And so we update in this direction with respect to some step size. So instead of just taking yk minus 1, which that would be the results of this if tk was equal to 1, that would be like a pure proximal Newton method. We actually do some step size optimization like a backtracking line search, and instead update along the direction given by y. I'm sorry, it's also a typo, probably confusing to you guys. This is supposed to say xk is equal to xk minus 1 plus tk times, this is important, yk minus xk minus 1. Okay, so that's supposed to be a yk. Just a typo in the slides. Okay, so that's Proximal Newton method. When I said, sorry, let's just leave it at that. Any questions about that? Okay, so I think it's very much in line with what you learned from proximal gradient and Newton. It's like a happy marriage of those two ideas. It's not too surprising given that you've seen both of those two ideas. So just go back to the motivation slide. Let's just check this is actually minimizing a quadratic approximation of the Hessian. Not hard to do. Just plug in for y. Right? Y is the kind of intermediate update that we form before we do the step size optimization. It's given by the minimizer over all z of the Newton step with respect to g minus c squared in the h norm plus h of z. And if we expand that out, recalling that the h norm is defined by something transpose h times that something, then we can see that we're going to get a term that looks like g transpose z minus x. It's because there was an h inverse associated with grad g and then an h from the norm. So the h canceled. And the quadratic term here is x minus c transpose h transpose x minus c times a half. That's this quadratic term, and then the h just carries forward. So this is indeed minimizing a quadratic approximation to g plus h, but this quadratic approximation uses the full Hessian rather than using just an identity matrix times a constant. Okay, so just a few notes. If we take h to be 0, we get back the usual Newton update. Just like proximal gradient, when h is 0 gives us back the usual gradient descent update. When h is positive definite, strictly positive definite, you can check that this scaled proximal mapping retains many of the nice properties of unscaled proximal mappings. So we learned a bunch of properties of the prox. There was actually a bunch we didn't cover as well. Proximal operators are kind of they generalize the notion of projection. So they inherit a lot of the properties of projections. Remember that projection is a special case of the proximal operator when h is just equal to the indicator function for a particular set. These also retain some of those properties, these scaled proximal mappings. And this is a recent paper that studied some of that stuff. Nice paper by Jason Lee and some of his co-authors. For one very basic property is that it's well defined when h is positive definite because the minimizer is unique. When h is positive definite, this is a strictly convex criterion. So the minimizer over all z is unique. So it's a well-defined operator. If h is positive semi-definite, then it's no longer necessarily well-defined, and the operator itself is not necessarily well-defined. But when we apply Newton's method, we think about the Hessian being invertible everywhere. So that's the same territory here. We think about h being positive definite. This is a big difference now. So those were similarities between proximal gradient and proximal Newton. This is a big difference between the two. The difficulty of the prox has mostly to do with h, although g now plays a role. Right? G plays a role through the Hessian, through its Hessian. So if I asked you to apply proximal Newton method to g plus h, and g was a matrix g was a function that always admitted a diagonal Hessian, that makes this scaled prox very easy, potentially, because it's basically just a little different from the unscaled prox, right? Now it's a diagonal matrix, and its diagonal entries may be different, but you might imagine that would make computing this a lot easier. However, if I gave you a g that had, for example, a fully dense Hessian everywhere, that makes this problem much harder. So g sneaks in there. It plays a role through its Hessian, unlike proximal gradient, where it essentially plays no role. Did you have a question?
Yeah, I was just wondering so there's no way that here the inverse of the Hessian nicely disappears, but when we apply the proximal mapping, so in those iterative steps, we always need to compute the inverse. There's no way that it disappears. Or?
Oh, it does disappear. So this was just notation. This was just notation in terms of the scaled prox. You mean this h inverse?
Yeah.
So this is a mathematical equality, but it turns out also to be equivalent to this line. See, y is also given by the second line. There's no h inverse in that second line. But when I write it in terms of the scaled prox, it's just which requires the h norm, it requires me to put an h inverse there. That's it. Yeah, so it's a good question. I mean, we're going to talk more about this step in a second. I just wanted to point out at a high level that now G plays a role, and potentially an important one as well.
H maybe depend on X.
Sorry?
H depends on X. The Hessian matrix depends on the point X.
Yes, right?
But when we write proximal, we do not use this X. We use X minus H inverse and gradient. We call this in total X. But this one will be different from the X using H.
I don't understand. I don't think that's true, what you're saying. So, like, look at these here. This is the Hessian of G evaluated at xk minus 1. I'm taking now exactly a Newton step with respect to G at xk minus 1. So that everything is as expected. Okay. Yeah.
Where's the t? Because in the scaled proximal operator, we have the t.
Yeah.
This one.
It's a good question. So, so T appears in the backtracking line search we do, but it doesn't appear in the evaluation of the prox. So I guess you could attribute that to a fundamental difference between Newton's method and gradient descent, which is that if I write down a quadratic approximation in the Hessian, that is a valid quadratic approximation without any parameter. Right? This does approximate G. But with the gradient, if I'm getting rid of H and I'm putting an identity matrix there, then I need to know something about the function in order for that to be a valid quadratic approximation, and that's what T controls for. All good questions, yeah. So the H norm is just notation to make this look like the original definition of proximal operator. If you want, you can always remember this line, okay, which came from our motivation. This line is just telling you that you're going to do a quadratic approximation to G, but use the Hessian. So you can take this as a definition if you want, and then update x plus to be x plus t times y minus x for some t. I just used the H norm so that we could write it like basically as in terms of a proximal operator. That's it. Yeah. It's the same as pure Newton's method, so it won't always converge. But the proofs for convergence here are similar to those for Newton's method, where you prove that there is some region at which backtracking always chooses t equals 1 and it gets local quadratic convergence. So well, without it won't necessarily converge, like Newton's method. If you just start with pure Newton's method from the get-go, it could diverge. Yeah, we'll talk about the guarantees in just a bit. Okay, all good questions. So, okay, let's just jump ahead to backtracking. It's not obvious how to apply backtracking for this proximal Newton method. There are various ways to do it. This idea, by the way, proximal Newton method, the idea of quadratic expansion to smooth part is quite old. So it's not a new method. But this paper by Lee and others was quite new, and it kind of revisited proximal gradient in the modern kind of statistics, machine learning, optimization age. And it proved a bunch of rigorous properties about it, a bunch of nice properties. And one of the things that they proposed was this version of backtracking that has you avoid recomputing the prox at every inner iteration of backtracking. Okay, because that would be extremely expensive if you had to recompute this prox. So here's the idea. You start with backtracking parameters just like you do in backtracking for, say, regular Newton or proximal gradient, alpha and beta, and you evaluate the scaled prox once. Okay, so I take this, this proximal update, and I subtract off x, and now the direction in which I'm thinking to make the update is given by v. So this is y minus x, or we called y this thing, the second line there. So it's just y minus x. And I start with t equals 1, which would be a pure Newton step. And again, same as I said with Newton, starting at t equals 1 actually has meaning here. Okay, that corresponds to like the pure Newton version of this. It's the largest possible we can make the step size, unlike backtracking for proximal gradient, where you start is kind of arbitrary in terms of the backtracking loop. You always start at t equals 1 here for backtracking. And you check whether or not the criterion at x plus tv is bigger than f of x plus alpha times t grad g plus v, plus the difference in penalties. That d is supposed to be a v. It's supposed to be x plus tv. Okay, so unlike what we've done before, you can see that here I've tried to achieve something close to what we get if we take a linear extrapolation of g, but then also what we get if we just were to move in the direction of v with respect to h. We've treated those two terms separately. Okay, so the advantage of this is that I don't have to recompute the prox. So this v is constant throughout these inner iterations. So if this is not met, then I just shrink t to be beta times t, and I check that again, and et cetera, et cetera. The advantage is that I don't have to recompute the prox. Okay, whereas if you look back at our notes for proximal gradient descent, you should convince yourself this is the case. Every inner iteration of proximal gradient descent, this backtracking loop requires recomputing the prox. So there's a big difference in cost. You can guess why we do this. It's because the scaled prox here is much more expensive than the scaled prox for gradient descent. Okay.
Does it mean that we will shrink t many times in one iteration?
Do you mean is this going to be as efficient as doing, like in terms of finding a good value of t? Well, I didn't understand the question.
I just say that if we check this and we shrink t, like we shrink only one time each iteration or many times.
No, we repeat this until we meet this criterion. So you repeat this, check, shrink t by a factor beta if it's not met, and then check again and shrink t if it's not met until that criterion is met. The extra criterion is met, just like regular backtracking. Yeah, William.
So could we have used the same type of strategy on proximal gradient descent, or is it specific for?
Yeah, it's not specific. So the difference here is that I'm not recomputing, say, the actually, it's a good question. I'm actually not sure if this would work for proximal gradient, because for proximal gradient, t is kind of t is tied into the definition of the proximal operator, wherever that was, and we can't really get rid of that. But you can see with proximal Newton, as was pointed out, there's no appearance of t here, right? Because the expansion is in the Hessian. So I would guess you could. You could forget about the fact we're doing proximal Newton, and you could just evaluate the prox once, and don't change that update direction every time you do backtracking, and just shrink the parameter. Practically, I don't think there's any problem with that. I just don't know if we have the same guarantees for it. I'm not aware of it. Yeah, it's a good question. I mean, it'd be certainly something to try for an expensive prox operator for proximal gradient. Yeah.
Something fundamentally different from proximal gradient, despite the approximating the hedging linearity, and then t potential.
Right. Although t is also scaling the update here, so I'm not sure if you would be able to make up for it. So the problem is that in every inner iteration of backtracking for proximal gradient, you're not necessarily looking at the right direction because you've just checked for the update direction once, but you're also scaling down its magnitude quite a bit as you go along. So yeah, backtracking for some of these more specialized methods like proximal gradient and proximal Newton, it's not a standard agreement about how to do them. So you'll find different papers proposing different methods. Yeah.
But it wouldn't really save you anything because in proximal gradient the cost comes from evaluating h, right? And here you're doing that gapping. So even if you're not re-evaluating the prox.
For proximal gradient, it would save you quite a lot because, for example, for if h was, for example, the trace norm, we saw that the prox operator was like a partial SVD. It required a partial SVD. So if the process is expensive, then yeah, doing like something like this for proximal gradient might not be a bad idea. But you're right in that most of the time we apply proximal gradient, we don't actually use like terribly difficult prox operators. So for like the L1 norm, it wouldn't matter. It's the difference of like a soft threshold or not. So it's not going to change much. OK, all good questions. So we need to back up a bit and just see if this makes sense. We've been talking about the mechanics of proximal Newton, but we haven't really been talking about the philosophy when you use it. So let's talk about that, and then let's take a break. One of the main drivers behind proximal gradient descent, if you recall, was that we can transform this problem, right, minimize g of x plus h of x, into a sequence of quite easy problems, where g is basically replaced by a least squares loss, where it's just some constant b minus x squared. That's how you think of proximal gradient, right? We take a quadratic approximation to this. Essentially, the only term that matters is this guy, right? Some constant b minus x squared. And provided I can solve this problem easily, minimize over all x b minus x squared plus h of x, that's actually the prox operator for h, then I'm in good shape because I just do that iteratively and b changes each time, and that's how I solve this problem. So I reduce this problem to a sequence of easier problems, each one of which replaces g by something that looks like this. Here we've done something similar, but we've actually replaced g by something like this, b transpose x plus x transpose ax. So it's no longer a simple quadratic. It's actually, it can be a fairly complicated quadratic. And similarly, we solve this problem, minimize b transpose x plus x transpose ax plus h of x. That's the scaled prox, where a is the parameter. And then we update b and a, and we do it again until we get the solution to our original problem. But if a was dense, then you may think this would be rarely easy, right? So if a is dense, then just solving that inner problem, that proximal, scaled proximal problem, would be a pretty difficult subproblem. Right? It would not be cheap at all. It would not be like soft thresholding. To convince yourself of that, just think about h being the L1 norm. What happens if I try to apply proximal Newton to a problem in which h is the L1 norm? What do I get? What's the name of that subproblem? It's just a lasso, right? It's a pretty hard problem. We've already encountered that problem itself from an optimization perspective. So that's not something we'd want to do very many times, right? We wouldn't want to have to try to solve the lasso as an inner problem. That seems extremely expensive. So what we should hope for, if we're going to be using proximal Newton, is that the convergence rate of proximal Newton, in terms of the number of outer iterations, the number of prox evaluations I need to make, is something akin to what Newton method would achieve. So hopefully like 5 or 10 when I'm in a good spot, and not very many for me to get there. And that ends up being true for a lot of problems. And that's really the philosophy behind proximal Newton. Very different from the philosophy behind proximal gradient. OK, so proximal Newton, it's used when we think we have a really good solver for the scaled prox. And these are almost never analytic solvers. They're things that typically require another optimization. Like, for example, I might do proximal gradient just to evaluate the scaled prox if I used h to be the L1 norm, right? That might be my go-to method. And I hope that in doing so, I can get away with only maybe 5 or 6 outer iterations, which is kind of similar to the speed of Newton, or maybe 15 or 20 outer iterations, to be more realistic, so that I solve the original problem with some efficiency. Now, if that wasn't true, I'd be in a lot of trouble, because if I was applying Proximal Newton in a case where the prox was very hard to solve and the convergence was pretty slow, then I'd just be in a bad spot. So in other words, you should be applying Proximal Newton with care. Unlike proximal gradient, it can be really efficient sometimes or really inefficient other times, depending on, it all depends on how well you can solve this, this scaled prox and what kind of techniques you can bring to the table to do so. These are optimization routines, not like analytic solutions. Okay, questions about that motivation? Yeah.
Oh, sorry. No, not really about the motivation. Are we going to have different phases of convergence again? Or
Yes. I don't remember if I put down the. Yeah, I think I put down a result for, that we'll get to, but I didn't write down the specifics of how it's proved, but it's similar in the sense that there is a quadratic convergence phase, and there is a I'm not sure what the damped phase, where you start choosing the step size to be quite small, and that's how the proof proceeds. If you're interested, you can see that Lee paper. They proved that as well. Yeah. Would it make sense? Let me ask you this question as, you know, test of understanding. Would it make sense to apply? Like, let's suppose I wanted to solve logistic regression with an L1 penalty. So that's my example. I want to solve something like the logistic loss plus lambda times the L1 norm of beta. Would it make sense to apply proximal Newton method here? Or when would it make sense to apply proximal Newton method here? So if I apply proximal gradient directly, then I will require something like, let's say without acceleration and without strong convexity, I require something like order 1 over epsilon iterations, right? Each iteration being very cheap. It's like a soft threshold to get an epsilon subaccurate solution. Proximal Newton, what happens if I use proximal gradient for the inner step? What would the cost be there? Each inner step would then take order 1 over epsilon iterations. So just to solve one iteration, to compute one proximal evaluation takes about as long as it would take to solve an entire problem with proximal gradient. Seems like a terrible trade-off. Then on top of that, we'd probably be doing something like 15 of 20 of those in the best case. So, you know, there's this plus outer iterations. So it's not a good trade-off. That's our conclusion. So why at a high level was this not a good idea? Can anybody point that out? So it was because we used proximal gradient in here, but why was proximal gradient a poor choice? It wasn't a very specific question, but you guys can think about it. Yeah. Yeah, I mean, so it's not very fast. It's true. It doesn't. I mean, you're saying this is not a very fast convergence, right? That's true. But there's something maybe more important about this example. Proximal gradient already applies equally well to logistic loss or quadratic loss, like this thing. So proximal gradient doesn't care if the loss is this or if it's logistic. It works just as well in each case. So that's not the thing you want to be using in the inner loop of a proximal Newton method. You want to be using something that's very specialized to quadratic loss. It does very well in the case of quadratic loss, and maybe can't be applied directly to logistic loss like this one. Otherwise, there's no point, right? Because you could have done proximal gradient on the outer loop. So you don't want to apply a method on the inner loop that can already be applied to the original problem with the same speed. Then you're already putting yourself at a disadvantage. So what we want to use here is a lasso solver that's very specific to quadratic loss, and that does very well in terms of quadratic loss and can't handle logistic loss. If we can do that, then it may make sense, because even though this is 1 over epsilon, we may get something much better here because we're only going to be thinking about quadratic loss. So what we care about is that the method we use in the inner loop gets a good convergence rate, but only for quadratic loss. So can anybody guess what such a method is going to be? It's not something we've covered so far, but this is what's typically done in practice. I'm not aware of, that sounds like an interesting suggestion. I'm not really aware of people doing that. Yeah. Yeah, coordinate descent. So we'll cover that in good detail at the end of the course, but coordinate descent is a method that can be done very efficiently, but it's specific to a quadratic loss. It does not work for logistic loss directly. Okay, so that's what people do when they apply proximal Newton. On a problem like this, they use coordinate descent for the inner loop, and that's much faster than 1 over epsilon, because it's only specific, right, to solving a quadratic loss problem. Okay, let's take a break, and then we will come back and finish off the rest.